Hi everyone, welcome to video 21-4A. We're going to be working with what's called mutually exclusive and overlapping events. And depending on which type of events that we have, we're going to calculate the probabilities throughout this section a little differently. So our first video here is working on page 1119, and in the Explore we have our new definition here for mutually exclusive events. So if we're doing something mutually, that means both, and then exclusive means are left out, and it's sort of like both events are left out of each other's groupings. So meaning that they cannot both occur in the same trial of an experiment. It's impossible for both conditions to be satisfied, basically. So as an example, they say if we flip a coin, it can't land both heads up and tails up in the same trial, and therefore we would say the events are mutually exclusive. So to talk through how we would calculate the probability if we have mutually exclusive events, in part A here we have let A be the event that you roll an even number when you are rolling, as you can see here, a dodecahedron, and that has 12 sides, as you can see. So what we want to do is fill in this Venn diagram by writing where all the outcomes would be. So event A is rolling an even number, and event B is rolling a 7. Okay, so let's zoom in a little bit on this Venn diagram and write in our values. Event A is an even number, so we're going to write all the even numbers in the span from 1 to 12, which is, of course, 2, 4, 6, 8, 10, and 12. Then event B is rolling a 7, so in circle B we have 7. And if you'll notice, in this region right here, which is both A and B are occurring at the same time, we can't have a number fall in both of those conditions. A 7 is not even, and even numbers are never 7. So just to fill in the rest of our sample space, all the other odd numbers that are not 7, so 1, 3, 5, 9, and 11 would be there. Okay, so that's filling in our diagram. Now if we zoom back out, we can talk about calculating the probabilities that we're looking for here. So to calculate the probability of A, as you know, we're going to count up the number of items in the event A and over the total in the sample space. Well, every time we're rolling a dodecahedron here, we have 12 as our sample space. Sorry, having stylus issues. And if we count up the number of values in circle A, or event A, it's 1, 2, 3, 4, 5, 6 different values. So that is 6 out of 12, or 1/2 when we reduce. And I'm going to give you a strategy here, you guys. I would actually wait to reduce until the very end of your calculation, because common denominators, as you see here, keeping the 12 for the total sample space is going to be important. So part C, calculate the probability of B. That's just one possible choice, the number 7 out of the 12 that we have. And then D is calculate the probability of A or B. And if you remember the or, it's where all of the values are shaded in. Everybody gets to come to the party, everybody's happy. Again, the number in the sample space here is 12. The number of items in A or B, which remember is all of this almost MasterCard looking logo here, circles overlapping all together. Well, that's 6 from circle A and 1 from circle B, or 7 values altogether. And so that's 7 out of 12. So for part E, we're basically taking a look at and making a comparison. It says calculate the probability of A plus the probability of B. Probability of A is just, as you know, 6/12. And again, I'm putting this back in its non-simplified form on purpose, because look, now we have our common denominators here, okay? So when we add those together, we do get 7 out of 12, which is the exact same thing as the probability of A or B. So we would put an equal sign in that final row there on page 1119. Okay, so we're headed towards kind of a pattern for mutually exclusive events when we are able to calculate their probabilities. Let's go to the next page. On the next page, in Explore 2, we see that we definitely have a definition here. If the events A and B are mutually exclusive, then the probability of one or the other is very simply just the probability of each of them added up. So this is what we call the addition rule. The two events are overlapping, or sometimes called inclusive events, though, if they have one or more outcomes in common. So I'm just going to draw a line here, and I would encourage you to do the same. This next example on the bottom of page 1120, is showing overlapping events, and mutually exclusive was just the last little bit. So if you draw a line there, you'll know that that's separating the notes from one type and the other, okay? So what is the probability here in letter A that we roll a number on a dodecahedron and the result is an even number or a number greater than 7? So again, let's go through and create our Venn diagram and put the values where they belong here. And I'll just remind you that a dodecahedron, remember, is a 12-sided figure. So in A, as we zoom in, A is the event that we roll an even number. Now that should be familiar to you. I'm going to suggest that you write the sets before you put them onto the Venn diagram, kind of off to the side here. So here's my set A. Even numbers, 2, 4, 6, 8, 10, and 12 on our dodecahedron. And then event B is a number greater than 7. So of course that's starting at 8, 9, 10, 11, and 12. Oops, 12. What we want to do is we want to complete the Venn diagram by figuring out if there's overlapping trials in each of these events, putting that in the overlapped section first, and then filling in all the other values. So I hope you guys can see that the number 8 here is used in both. The number 10 is used in both sets, and the number 12 is used in both sets. So as far as the overlap section in our Venn diagram, you want to start by putting those 3 numbers there. Then the rest of the evens can go in circle A, 2, 4, and 6. And then in circle B will be the rest of the rest of the numbers from set B that are not already in the overlap. So that's 9 and 11. Filling in the rest of the sample space, which is not in either of those events, we have 1, 3, 5, and 7, which is outside of both circles. Okay, so let's go over to page 1120, the facing page here. So in part B here, we're calculating the probability of event A. I'm just going to pull off our Venn diagram from the side here so we can count up those choices in circle A. So circle A has 1, 2, 3, 4, 5, 6 choices with even numbers that hopefully that makes sense. So that's 6 out of 12, and again we can go ahead and simplify that fraction, but I'm going to probably suggest that we take a look at the non-simplified version until we're done with our calculations. Okay, let's look at what's next here. Calculate the probability of B. So now we're going to take a look at circle B has how many choices? 1, 2, 3, 4, 5 in that full circle, and so that is 5 out of 12. And then part D is going to ask us to find the probability of A and B. Remember, whenever we have and here, that's the same as an intersection, or the overlap, which is the name of the section, right? Overlapping events. We can see that the values 8, 10, and 12 are in that overlapping section. So that's 3 different values out of 12, or we can simplify that to 1/4. Part E says, now use that Venn diagram to find the probability of A or B. And using the Venn diagram again is counting up the values that are in the complete total circles here of 1, 2, 3, 4, 5, 6, 7, 8 out of 12 outcomes, and reducing that to 2/3. Okay, so now F is the part where we kind of get to the kicker here, you guys. So part F says, great, now that I have those outcomes, we're going to use the probability of A, B, A and B, all 3 of those pieces, to calculate the probability of A or B. So in other words, what could I do with 6, 5, and 3 and get 8 out of it? Well, the probability of A, remember, is 6/12. The probability of B is 5/12. And the probability of A and B is 3/12. So I hope you guys can see that if we added the 2 separate probabilities, A and B, and then subtracted the overlapping section's probability, A and B, trying to get a 12 down there for you, sorry, that would give you 8 out of 12, or 2/3, for your final probability of A or B. Okay, so as we go to moving on here, whenever we find an OR probability of overlapping events, we have the addition rule under explain 1. Let's take a look at that. And that is going to be that the probability of, in overlapping events, A or B, is going to lead to the probability of A separate plus the probability of B separate, and then minus the probability that they share in common, because otherwise we're basically counting this overlapping section twice more than we should. So this is a really important addition rule here, and it works whether it's mutually exclusive or overlapping, because if it's mutually exclusive, this last part would just be equal to 0, and then we're back to the addition rule we had to begin with. Okay? In the next video, we're going to talk about how to use this addition rule when we are looking at what's called a two-way table of data. So that's video 21-4B coming up next. We'll see you guys next time.